All right, so this is the last talk of the day. So right now, please tell me if I'm butchering your name, but so Fedor Sandomirskiy is going to talk about not private information, but private information. So,
thank you, Juba, and thank you all for staying until the very end. I feel extra responsibility. I'm Fedor, a postdoc at Caltech, and this is a joint work with Kevin He from UPenn and Omer Tamuz from Caltech. In this paper, we are interested in the following general question: how to disclose information optimally if we are restricted by some privacy constraints. And to clarify what I mean by that, I will describe the model right away. It's a very basic toy model. So we have an agent, and for simplicity, we have a binary state, either low or high, and our agents attribute the same common prior probability to the event that the state is high, probability P. Also, each agent I gets a signal Si from her set of signals as capital I. It's just a random variable arbitrarily correlated with omega, and the signal constitutes the private information that our agent has. However, even though we call it private information, it may not be private. For example, the signal that is received by agent I may carry some information about the signal of agent J. And to show you the most extreme example, public signals is a particular case of this setting. So if all the agents get exactly the same signal, it's a particular case, but clearly in this situation, each agent knows what other agents learn from their information. So private information may not be private. And we are interested in the situation when agent's signal tell our agent something about the state, but tell nothing about what other agents learn about the state. So we give the following definition. So a joint distribution of omega, the state, the collection of all signals, is a private information structure if signals are independent. And by independent, I mean unconditionally independent. So if I observe my signal, I can say nothing about the realization of signals of other agents. So these signals may carry some information about the state, but they do not carry any information about each other. So they keep higher order beliefs trivial. And of course, the first question to ask about this setting, whether it is at all possible for agents, for different agents, to get informative private signals. And this question may seem to be counterintuitive, because how can it be that S1, the signal of the first agent, is correlated with omega? Omega is also correlated with S2, the signal of the second agent. And yet, the first agent learns nothing about the realization of S2 from her own signal S1. Despite this intuition, we will see that actually it is possible, but this intuition is correct in the sense that there is a tension between informativeness and privacy. And our goal is to understand what are the most informative signals given this privacy constraint. So what do I mean by most informative? So how to compare informativeness? What does it mean that a signal S is more informative than a signal S prime? To answer this question, let's denote by P of S the posterior belief induced by signal S. So it's just the conditional probability of the high state given this signal. And by itself, it's a random variable with values in 0, 1, just because it depends on signal S, which is random. So the posterior belief is a random variable. Now we say that a signal S, Blackwell dominates signal S prime, or Blackwell more informative than S prime, if for any convex function phi on 0, 1, the expected value of phi of the posterior induced by the first signal is greater or equal than the expected value of phi of the posterior of the other signal. So it's a formal definition. It's rather handy, but it's not the reason to love this definition. The reason to love this definition is its equivalent form. So it turns out that this notion captures the following property. So S is more informative than S prime if in any decision problem the signal S gives higher or equal utility to the decision maker than S prime. This is the reason why this Blackwell order is used everywhere in economics. Okay, so we've learned how to compare signals. Now we compare information structures. So one information structure dominates another if each agent signal in the first structure dominates her signal in the second structure. This gives us a certain partial order on information structures, and so we can look at its maximal elements. So a private structure is Pareto optimal if it's not dominated by another private structure. And our goal is to characterize these structures. It turns out that if we have just two agents, there is a very simple answer. So characterization for two agents. So consider a cumulative distribution function f on 0, 1 with min p, and p is our prior probability of the high state. We can define f hat by the following formula. And what happens here is easier to illustrate in a picture. So it turns out that f hat is what we get if we reflect the graph of f with respect to the anti-diagonal. In particular, f hat is also a CDF, and it also has min p. We will call the pair f and f hat conjugates. And here is our result. So for two agents, a private information structure is Pareto optimal if and only if the belief distributions induced by signals of the first agent and signals of the second agent are conjugates. So a very simple test of Pareto optimality. And moreover, this theorem is constructive in a sense that if you give me a pair of conjugate distributions, I can construct the corresponding information structure. Good. Let's say a few words about applications of this theorem. So imagine Amiga capturing borrower's creditworthiness, and for simplicity, again, it's either low or high. And S1 is a private, legally protected trait of this borrower, and as it sometimes happens, S1 is actually correlated with Amiga. We have a rating agency who actually has all the information about the borrower. It knows both Amiga and S1. And the rating agency wants to send an informative signal S2 about creditworthiness, maybe to a bank. But this rating agency can be restricted by some privacy laws that require S2, the signal about creditworthiness, to carry no information about this private trait S1. And this requirement is equivalent to what's called demographic parity in Fair classification. So the question becomes to find the most informative signal S2 under these privacy constraints. So we want to find S2 maximally informative about omega, but independent of S1. But now we can reformulate this goal the following way. We want to find a Pareto optimal private information structure, omega S1, S2, with given marginal on omega and S1. And using the theorem from the previous slide, we get the following corollary. So for given omega and S1, optimal S2 is unique in the following sense. There exists S2 that dominates any other signal S2 prime that is independent of S1. And not surprisingly, the beliefs induced by S1 and S2 are conjugates. I want to stress that this uniqueness is a very surprising property because Blackwell order is a partial order. And typically, if you have a partial order, you have many maximal elements. So here, it means that the most informative signal is unique. In other words, for any decision maker, this signal will be optimal. So the rating agency does not need to know how the bank is going to use this signal to come up with the best signal for the bank. And this becomes additionally surprising because it turns out that for 3 and more states omega, you may have a continuum of incomparable optimal signals S2. So for 3 and more signals, it's important to know the objective of the decision maker to supply the best signal. OK, now I want to talk a little bit about the ideas behind these results. And I think it's the most rock and roll part of this paper. First of all, these results rely on a certain canonical representation of private information structures. So let's take a set A, a subset of the n-dimensional unit cube with measure P. And what I want to define is a private information structure associated with this set A. It is constructed the following way. So if the state is high, we sample the collection of signals uniformly from the set A. And if the state is low, we sample the collection of signals uniformly from the complement of A. What's nice about that is that signals, as a result, they are unconditionally uniformly distributed on the unit cube. And so they are independent. We get privacy for free in this construction. So no matter what is the set A, this gives us a private information structure. And so, for example, you can take the blue set A, like in this picture. And actually, it's very easy to compute what kind of beliefs the corresponding structure induces. So for example, I'm the first agent, and I get signal S1 that is equal to this particular point. Then my belief induced by this signal is just the fraction of the blue set in the corresponding vertical slice. In particular, this information structure induces belief that are uniform on 0, 1. You can take another blue set. So this one induces beliefs 1/4 and 3/4. You can also take your favorite set. So we can generate many examples. And the question is whether we get a large family of examples or we get everything. And it turns out that we get everything. So any private information structure is equivalent to the one associated with some set A. So it's
The picture doesn't seem to have the same measure as the first. The picture doesn't have the same measure as the first.
True, it corresponds to another prior. Why not? Okay, so this representation is one ingredient. Let me tell you about another. Another ingredient is tomography. So what's tomography? Tomography is a science that allows you to reconstruct multi-dimensional objects, maybe three-dimensional objects, from their lower dimensional projections. So like you have this bone, and you project it in one direction, in another direction, and you try to reconstruct the form of this bone from these two projections. And we need the following notion from mathematical tomography. A subset A from the n-dimensional unit cube is a set of uniqueness if this set can be uniquely reconstructed from its n-coordinate projections. So formally, we look at the Lebesgue measure restricted to this set, and we compute its one-dimensional marginals. And the set is the set of uniqueness if there is only one set up to, of course, zero measure, up to zero measure that leads to these projections. Our second main result is the following theorem. It holds for any number of states, any number of agents. A private information structure is Pareto optimal if it is equivalent to a structure associated with a set of uniqueness. And luckily for us, in the case of two agents, there is a nice characterization of sets of uniqueness. So it turns out that in the dimension 2, a set is a set of uniqueness if it is upward closed. So with each point, it also contains all the points with higher or equal coordinates. Or it can be made upward closed by a measure preserving transformation of the axis. And combining these two theorems, we get the characterization that I mentioned before via conjugates. OK, so to conclude, private information structures capture the situation when we want to supply information to the agents and keep them agnostic about what other agents know. It turns out that these structures can be represented as subsets of n-dimensional unit cube. Those Pareto optimal structures, they correspond to a set of uniqueness, and using the known characterization of sets of uniqueness, we get a very simple criterion of Pareto optimality for two receivers. Thank you.
Right, we can take like maybe 2-3 questions right now, and this will be the end of the session. So yeah, does anyone have any questions? I guess I have a question. Then can you just go back like just a couple slides when you actually had the slide on tomography? I'm trying to understand the intuition there. So is it kind of like the intuition if I look at this picture, so for example, if I look at each dimension of this problem, I do get information about kind of like the picture in between, like what that set is going to look like. But if I just were to see what's on the kind of like x-axis here, that pretty much doesn't tell me what the projection on the y-axis is going to look like at all, and vice versa. Is that kind of like the intuition between the independence here, while you're still informative about both, or am I just completely making this up?
So kind of, is the question about the intuition behind this theorem too? Kind of why Pareto optimality is at all related to tomography?
Yeah, I guess my question is kind of vague, but to some extent, yes. Yeah.
So the idea roughly is the following one. So if you have two representations of the same information structure via two different sets, then you can build a new information structure by mixing these two. And this new mixed information structure will contain some extra randomness. This procedure of choosing between the first and the second. And using this extra randomness, you can actually construct an extra informative signal that you can reveal to one of the agents or somehow divide between the two agents and make a Pareto improvement. This is the idea, why uniqueness plays this role in Pareto optimality.
Okay, cool. Yeah, thanks a lot. Yeah, does anyone else have any question? If not, we can call it a night. It's already like almost 6:20, and people can go do whatever they want and have fun. Right, yeah.